All right, hi guys, we're back. We're talking about continuity today, but I wanted to break it up a little bit because I'm on a recording session, and I'm sure you're probably sometimes getting as bored watching these as I am making them. So here's my setup. You got Miss Harrington sitting on the floor in her guest bedroom, Christmas tree under the bed because coffee. There's my notes that I already filled out, colored pens. This is where I'm meeting you guys when I'm online. There's my little desk and my calculator that's probably going to run out of battery because I didn't bring home the charge bank. And then just stuff everywhere. So there we are. And this is the little iPad thing that I record from. And I spend so much time trying to not get a shadow, but I can't do it. You see, there's still a shadow no matter where I put it because the lights are right above. So hopefully you can still see it though. Okay, I'm trying my best. You give me some feedback. I know we're already like 6-7 videos in, but if you have specific feedback, let me know. So today we're talking about continuity, and we're talking about when a function is continuous. And you guys, I think, conceptually can understand when a function is continuous by looking at it, right? Is there a jump? Is there a break? Is there a hole? Then we know it's not. But we're going to use this. We need this formal definition because for further theorems, you cannot use those theorems unless the function is continuous. And so you have to check that the function is continuous by doing these three things. So in calculus, or in your math career, you will call a function continuous at a point x equals a. So let's say a function is continuous at a point x equals a, because we're really only having to talk about a point. If there is a value for f of a, right? F of a is defined. And then the limit as x approaches a exists, which means that the left limit matches the right limit, because you can say it exists. And then therefore, the final step is that the limit as x approaches a of f of x equals f of a. So the limit matches the y value. All of those three things have to be true for a function to be continuous. So let's check these two functions and let's see if they're continuous. Okay, the first example, it says f of x equals 1 over x plus 3. So I drew this function, right? So this is a rational function, and we've got a plus 3 being added to the x. So hopefully you remember that that's a horizontal translation to the left 3, which is why it's here. So the asymptote, instead of being at the y-axis, is now at x equals negative 3. And then there's the function. Okay, so let's check. If we make the point, we're going to say at x equals, we're going to check continuity at x equals negative 3. And I'm picking negative 3 because it's where that asymptote is. So first of all, let's check. What is f of negative 3? It doesn't exist, right? Because there's an asymptote there. So right away, we know it's not continuous. Number one, the first rule is out. But let's just check the other two. What is the limit as x approaches 3 from the left of f of x? Okay, from the left, it's negative infinity, which means it does not exist. And what about from the right? The limit as x approaches 3 from the right of f of x. From the right, well, it's going up, it's positive infinity, which also means that it does not exist. So our left and right limits don't match because they don't exist. Therefore, we know this thing isn't continuous. But the way the reason we're talking about this, because this is a discontinuous function, and it's a non-removable I'm going to spell this wrong. Discontinuous. So it's discontinuous, and it's a non-removable discontinuity at x equals negative 3, right? We can't get rid of that. This function is not going to be continuous at x equals negative 3. So then you're like, if that's non-removable, how can you remove a discontinuity? So that's going to bring us to our next one. Example 2. Example 2 is x squared minus 9 over x plus 3. So hopefully you remember from algebraic evaluation that if I'm seeing this, I can start thinking about how I can simplify this expression. So this is going to be in a different color so you can see. This is the same as, we're still going to evaluate the, we're going to look at the discontinuity at x equals negative 3. Okay, so let's go ahead and do this. I can rewrite this function, let's say f of x, as x minus 3 times x plus 3 over x plus 3, right? Why is that helpful? Well, it's helpful because now I can cancel these out, right? So now when I'm finding the limit, as x approaches negative 3 of x minus 3, because it's all that's left, well, if I plug in negative 3 minus negative 3 is negative 6, right? So it does have a value there. So now let's just check this with a graph. Okay, so if I'm graphing the function x minus 3, I already put this dot here to help me with, so you guys don't have to see me struggle through this looking at it on an iPad. But here is the point negative 3, negative 6, right? And I plotted it as a whole because x is still not allowed to be negative 3. I can look at my function up here and I know that's going to make it non-existent, right? DNE if I put a 0 down there. So it has to be a whole. And then what does the rest of the function look like? Well, hopefully you remember how to graph x equals x minus 3. So a linear function, it's going to have a y-intercept at minus 3, and the slope is, you know, up 1 over 1, but I don't really need that. I can just sketch it like this, right? So there's my function. Okay, so there's a hole here, but the rest of the function still exists. So what we would call this is a removable discontinuity at x equals minus 3, right? You can kind of ignore it. Because if I look at this, what's still the value of the limit from the left of negative 3? It's negative 6. What's the value of the right of the, what's the value of the limit as you approach negative 3 from the right? It's also negative 6. So these two, this second one is defined. It's negative 6. But then when I check number 1, is there an f of a? No, there is no value of the function at x equals negative 3. Therefore, this is discontinuous at x equals negative 3. Okay, but it's removable because we removed it right here by canceling it out. So discontinuities that occur where a limit exists can be removed by defining or redefining a point on the graph, right? So you can evaluate the limit at that point. So just like we did here, so the value of that limit is negative 6. And then if the limit exists, check that it equals f of a. And it doesn't. So it's still discontinuous, but you could still, you just know that that one's removable, right? So non-removable discontinuities are associated with jumps or asymptotes. So just like these examples, if there is a hole, that's a removable discontinuity. If there is an asymptote, like this infinite one we drew up here, that's also non-removable. If there is a jump, that's also non-removable. Why? Because the value of the limit from the left is different from the value of the limit as you approach from the right. So just knowing that some discontinuities are removable, some are non-removable, and these pictures should help you with that. All right, so I'm going to go on to the next page. I feel like I'm missing one. I went straight to example 3. Okay, here we go. Let's just do this one. Find the constant a such that f of x is continuous for all real numbers. So we want to make this function continuous. So f of x equals 2 of x if x is less than or equal to 1. And then f of x is equal to a times x squared plus 3 if x is greater than 1. Okay? So if I'm looking at this first thing, we're checking for it. We're trying to make this thing continuous. 1, f of a is defined. Well, what's f of a? Does it say for all? So we're going to find it at 1. Okay, let's find f of 1. Because that's where we're checking for continuity, right? We know 2x is continuous, and we know x squared plus 3 is going to be continuous. So what we're really checking is if it's continuous here at where it switches at 1. So what is f of 1? Well, f of 1, I have to use the top one, right? Because that's where it says it's less than or equal to 1. So that's 2 times 1, which is 2. Okay, now my second definition, or second point for the definition of continuity, is that the left and right limits match. So let's find the left and right limits at x equals 1 from the left. Let's do that first. So if I'm going from the left of 1, I know I need to use this. Okay, and that equals 2 times 1, which is 2. So I'm just going to rewrite this like this so you guys can see how you should be formally writing it. Okay, so the reason I draw this arrow, just so you know, is this is like an indication of here's where I'm doing my work to figure it out, because I'm not sure if it's equal to yet. Maybe something's going to happen. Oh, and yeah, I figured out it works, so now I'm rewriting it as it equals to. So this is like, here's the problem, here's my work. Now I can say they're formally equal to each other. Now let's do it from the right. From the right, it's going to be ax squared plus 3. All right, so doing my work on the side, that's going to be a times 1 squared plus 3, which comes out to be just a plus 3. Okay, so we need to figure out what this a is. That was the question, right? So we want this thing to be continuous, which means all three of them have to be equal. The left limit, the right limit, and the f of 1 need to be the same value. And so I can already tell f of 1 is 2. The value of the limit from the left is 2. So what does a have to be so that the value of the limit from the right is also 2? It has to be equal to 2. So 2 has to equal a plus 3 to make f of x continuous. So that's hopefully, I need to write on this, but I'll do it. So a has to equal -1. Okay, so there's our answer. If I plug in -1, the value of all of these three things is 2, making the function continuous. Okay, so, and then just a little reminder that you're going to have to remember horizontal versus vertical asymptotes, right? And I'm just going to write the note down here, and you can record it in your notebook because it's going to include a note on, and here, another spelling. I always put the P in the wrong place. Okay, so if you have, let's talk about vertical asymptotes first. A line x equals a is a vertical asymptote of y equals f of x if the limit as x approaches a from the right of f of x equals positive or negative infinity, or the limit as x approaches a from the right of f of x equals positive or negative infinity, which hopefully makes sense because that was our example here, right? If this was the value a, the point a, you can see it's a vertical asymptote. If you're approaching it from the left or the right, it's going to positive or negative infinity. So if you ever see that, you know that that's a vertical asymptote. And then for horizontal, a line y equals L is a horizontal asymptote of y equals f of x if the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And hopefully you remember that. Let me see if I can find my notes from the limits as they approach infinity. If they approach the same value towards positive or negative infinity, it's a horizontal asymptote. So that's like this example here. This is from that video on limits towards infinity, right? You can see that those are asymptotes because it's approaching 1 as you go towards infinity. It never crosses it. That's how you know it's a horizontal asymptote. Okay? So now you're going to do some practice problems to check if functions are continuous, how you can make them continuous, and are they removable or non-removable discontinuities if they have them. See you next time.